find the area of the largest rectangle that can be inscribed in a semicircle of radius r. Now, if you've never seen the word inscribed before, what this means is that we are putting one shape inside another so that their boundaries touch but don't cross over each other. Basically, we want the smaller shape to be fully inside the larger one, and they can touch, their boundaries can touch, but we can't have any bits of the inside shape going outside of the outside shape, if that makes sense. Anyways, let's jump in. We want to have a rectangle inscribed in a semicircle of radius r. Now, the easiest way to do that is to have our semicircle be centered at the origin and have it be in the first and second quadrants. Not the best drawing in the world, but this is the semicircle that's the top half of the circle, x squared plus y squared equals r squared. And we want to have a rectangle that is inscribed in it. So it's going to look something like this. And there's lots of rectangles that we could inscribe here. We could have one that's short and wide. We could have one that's really tall and narrow, and anything in between. But what we want to do is figure out amongst those different rectangles which one has the largest area. So to make life easy, what I'm going to do is I'm going to let the base of the rectangle be 2x. So we've got x on one side and x on the other, and the height be y. And then in this case, the area of that rectangle is base times height, which is 2x times y. So we want to maximize the area, but this is now a function of two variables, so we need to find a way to get rid of either x or y, to write one of those in terms of the other. But we know that whatever x and y are, we can draw in a radius here, and that tells us that x squared plus y squared has to be r squared, which is a rule because that point is on the circle, x squared plus y squared equals r squared. But we can take x squared plus y squared equals r squared, and we can solve for y in terms of x so that we can write that function all in terms of x. So to get y alone, we've got to get rid of that x squared term. So we subtract it to move it to the other side. And then we take the square root, giving us the square root of r squared minus x squared. And then when we plug that into the area function, we've got 2x times the square root of r squared minus x squared. Now, I know it looks like we've got a function of two variables, but we are considering r to be a constant, right? We don't know what the radius is, but that radius isn't changing in whatever diagram we've made. So that is going to be acting like a constant for us. And so we also know that x has to be between 0 and r, right? That width of the right half of the rectangle can't be negative, and it also can't be bigger than r, because then we would be outside of the rectangle. So we know that x is between 0 and r, and so we have a continuous differentiable function on a closed interval, so we can use the closed interval method, which means we need to find any critical numbers and evaluate the area at those critical numbers, and then also at the endpoints. So let's differentiate this to find critical numbers. dA over dx, and we've got to use the product rule. So we've got the derivative of the first times the second. The derivative of 2x is just 2. So it's going to be 2 times the square root of r squared minus x squared, plus the first 2x times the derivative of the second. The derivative of the square root of u is 1 over 2 root u. So that's 1 over 2 root r squared minus x squared, times the derivative of the inside, which is going to be negative 2x. Now, if we look at this, we can see that we can cancel out a pair of those 2's. So that makes life a little bit easier. And so we've got 2 times that square root. And then the next term is going to be negative because of this negative here. It's going to be minus 2x squared over the square root of r squared minus x squared. Now it's going to be advantageous for us to combine these into one fraction. To do that, we're going to need a common denominator, which is going to be this square root. But here's the interesting thing. When we multiply the top and bottom of the first fraction by the square root, we have that same square root in the numerator. So when we multiply it by itself, that square root is going to go away, and it's just going to be 2 times r squared minus x squared in the numerator. And then everything else is going to stay the same. And then if we combine these, we're going to have 2r squared minus 2x squared, and then minus another 2x squared. And so that's going to be 2r squared minus 4x squared all over the square root of r squared minus x squared. We're going to have a critical number when the numerator equals 0. So that's going to be 2r squared minus 4x squared equals 0. We can add 4x squared to both sides. We can divide by 4 because we want to figure out what x is in terms of r. So if we divide both sides by 4, that's going to give us r squared over 2 equals x squared. And then the square root of that is going to be r over root 2. So that is a critical number. And we also have to evaluate this at the endpoints of 0 and r. So we need to find the area at 0, the area at r, and the area at r over root 2. But the area at 0 and r, those are both going to be 0. Because if x is equal to 0, then there's going to be no width to this rectangle, and the area is going to be 0. And then if x is equal to r, that means that the width of this is the whole width of the semicircle, and that means there can be no height, so the area is also 0. So this critical number is going to have to be the one that gives us the maximum area. And so if we plug this in, we can plug it in right here. So that's going to be 2 times x, which is r over root 2, and then times the square root of r squared minus x squared. Well, x squared here is r squared over 2. And then inside that radical, r squared minus half r squared is just going to be half r squared. So we're going to have 2r over root 2 times the square root of r squared over 2. And that's going to give us 2r over root 2 times the square root of r squared is just r. So we've got r over root 2. And then the denominators, root 2 times root 2 is just 2. So we've got 2r squared over 2, which equals r squared. So the maximum area we can have for a rectangle inscribed in that semicircle is going to be r squared.